All right, it's time to start. It's 40 after. Today I'm going to go over that problem we did last time with the monkey and the hunter. Solve that formally, and I'm also trying to give you an intuition, just like the other three problems we did last time. I'm going to try to give you an intuition for why the answer turned out the way it was, why the tranquilizer dart did in fact hit the monkey, despite the fact that there was all this stuff flying around, and it doesn't seem obvious at the outset that that should be the case. Reading. Yeah, so reading we're doing is again not reaching. We're doing reading. Here we go. Reading chapter 3.1 to 3.5, and we're going to get to chapter 4 a little bit today. We're going to cover a lot next week, but we're going to get to it today, I think. All right. So today we're going to finish with projectile motion. It'll come up over and over, but we're going to finish with it as our primary topic of study. And we're going to move on to real physics. We're going to talk about Newton's laws at the end. All right? Very good. And one last time, I'll do a pitch for people. Early drop deadline is tomorrow. So if you're going to drop this class, you got to do it before midnight tomorrow. I hope you stay. But if you go past this deadline, then you have to do crazy things to try to get yourself out of the class. It's very hard after you pass that deadline. So what did we do last time? We had this set up where we had a cannon. We faced the cannon directly. I used a laser sighting. Right? I had a bore sighting. It was parallel with the bore of the cannon. And we put it right at that little stuffed animal I had up there, right? As cruel as it sounds. And then we said, all right, is it going to hit the monkey or not? So first of all, we have to decide before we formally solve this problem, what does it mean for it to hit the monkey? What has to happen? Well, we're going to define some axes in this problem, right? X and Y, it's a two-dimensional problem. And we're going to ask the question, if the ball hits the monkey, what does that mean? It means that the x value of the ball equals the x value of the monkey, right? And that's going to happen at some moment in time, if it happens at all. And then the second question is, well, does the y value equal the y value? The y value of the monkey equal the y value of the ball, right? So let's draw a picture of what I'm talking about. All right, so I'm going to make a nice, big, clear, hopefully clear picture. And let's do it this way. I'm going to draw it opposite of the way that you saw it from your perspective. Why am I doing that? I'm doing that in part because I'm used to drawing, I'm imagining myself in your shoes. Most of you are used to thinking of angles as going from the x-axis, which points to the right, up to some angle like that in the first quadrant. So that might be a more natural way to draw my angle theta. If you want to draw it the other way, that's fine. The physics is the same. This, of course, is a right angle. Here's my angle theta. The problem tells us theta. It tells us theta. It tells us how high the tree is. Maybe this is some height d, right? Maybe it tells us, oh yeah, the tree has a height d. Our monkey's up here. Maybe I'll put a little picture. Here's a little monkey face so I know that he's up there. That's what I mean by that point in space. Here's the cannon. I'll draw the cannon, right? I'll draw the projectile coming out, and I'll indicate its initial velocity or its initial speed. Well, I guess I could give it a vector on there. I'm saying what direction it's got. There's its initial velocity. Maybe it's given a name, capital V. So we're told in the problem description, here's how fast the projectile is moving right as it leaves the cannon. We're told the direction that it's going. It's pointing right at the monkey. We're told how tall the tree is. We're told how far away the tree is, the base of the tree is from our cannon. Right? Now, I drew the cannon with some physical extent so I can see it in my picture, but we're going to assume that this is very small compared to the other distances, so we can ignore that distance. But that's sort of a judgment call you have to make based on how the problem is worded. Right? Sometimes it'll be part of the problem, sometimes it won't. In this case, it's not part of the problem. We're just going to ignore the length of that cannon. But getting assumptions like that right in the beginning allows us to, like some students will perseverate on some little thing that's not important that winds up blowing them up. So in this problem, what are you assuming? We're assuming the cannon has no physical extent. We're pointing directly at the monkey to start. We have the initial velocity given for the projectile. We know these distances. And the question is, does ball hit monkey? Right? Does ball hit monkey? And so that's really asking, is x of the monkey at some time, we'll call it time hit. We'll just give it a name. We don't know if it exists yet. We don't know when it is yet, if it does exist. We'll say, does this equal x of ball at the same time, right? And these both have to be true. So that's not enough. I mean, let's think about that. Let's call this the x-axis. It's my x-axis. Let's make this my y-axis. Right? Let's make it tall enough, too, so I can indicate all the important places. This, well, let's see. If I call this 0, down here it's 0 for x and y, then this up here is going to be d, right? And this over here will be L on the x-axis. So the problem description doesn't tell us what labels to put on our axis. It just tells us the distance from here to here. And then once I choose my axis, okay, if that's 0, that's got to be L. Just make sure that your graph agrees with what they described in the problem, right? And the fact that I made this a positive x-axis, this had better be bigger than that is. And it is. There's positive L, there's 0. Great. Super. So that means given this, okay, x of the monkey at some time in the future called time hit, better equal to x of the ball. But it better also be the case that y at the same time, this has to be the same time now, right? Now think if we just ask the question, will this be true at some point in the future, if we use different times here than there, well, that could very well be true, but it doesn't necessarily mean the monkey gets hit by the ball, right? If the ball's flying out, so what's the ball going to do? It's going to follow some parabolic trajectory, right? And the monkey's going to follow its trajectory. And at some point, the x value, the horizontal position of the ball is going to equal the horizontal position of the monkey. That's inevitable, right? The ball's moving that way at a constant rate. It's just moving. Eventually, it's going to line up with the path of the monkey. But when that happens, the question is it also at the same height? Because that determines whether they hit. Okay, so I beat that dead horse. Let's go ahead and solve it. Well, so we're going to use our equations just like we did with the last set of problems we worked on. Are these two objects both undergoing constant acceleration? Is either of these objects not constantly accelerating? Well, nobody's answering. Yeah, they're both undergoing constant acceleration. That's right. So that means we can use those same set of equations. And in fact, I think I used the same one used last time over and over again. So let's write it out. Let's do it first for the monkey. The monkey's undergoing a pretty simple motion. It's just a one-dimensional motion. So I'll start with him. It's easier. Let's do the x direction first. And I'll say, okay, what's going on? Well, in the x direction, x monkey equals x monkey not. X monkey not. What is that? Oh, it's going to be L, right? Maybe I'll just substitute these in as I go if you guys are comfortable with that. So I'll say, all right, the position of the monkey is going to be L plus, but what's it going to be? Well, what is the initial velocity of the monkey in the x direction? 0. He doesn't move in the x direction. What's his acceleration in the x direction? 0. So all this stuff is just 0. In fact, this is the whole equation I need. X of monkey equals L. Pretty easy. What about in the y direction? Well, in the y direction, he starts off at an initial y value of positive d, right? And then what's his initial velocity? So he started from rest. So what's his initial y component of his velocity? 0. So what equation am I plugging in here? You all know what this is, right? You read it right here. I'm using that equation that says x equals x naught. This is for constant acceleration. Right? X equals x naught plus v naught in the x direction times t plus 1/2 a in the x direction times t squared. And I'm just plugging it in for y. I'm using the same equation for y. I'm just doing that right now. So d is the x naught, well, the y naught part. And then we said the velocity equals 0, so there's no term there. The acceleration, though, what's the acceleration in the y direction for the monkey? Negative g, where g is positive 10 meters per second squared. That's right. So it's negative 1/2 g times t squared. Great. So that describes the monkey's motion for the entire problem. Once after time 0, after the moment when he releases. Before that, this isn't describing his motion. He's not moving at all. So this would be 0. Here we see d. Okay, great. So now about the ball. So in the x direction, what's going on? Well, x of the ball equals the initial x value of the ball, which is 0, right? And then what do we add? We add its initial velocity, but we need its initial x component to the velocity. So we've got an angle in this problem. We're given the problem description v. So just like last time, we broke up the acceleration of gravity vector into two components. Now we're going to break up the velocity into two components. I usually draw a separate triangle to do this. In office hours, last time I said, oh, you drew a separate triangle at the time, confuse me. Well, if you want, you can do it right here. So I could just do it right here. I could just say, here's my vector, and draw it right on top of the diagram I've already got. I find it to be confusing, so I tend to, it just gets too jumbled. So I tend to just redraw it. But when I do it, I'm careful to preserve my, I'm pretty careful, to preserve my angles. So I want this to be a right angle, I want this to be theta. And I think I mentioned this last time. When we had this thing set up in front of the class, the cannon may have been at an angle of 45 degrees. I don't even remember. I think it's probably less than like 30 degrees. But even if it were at 45 degrees, as it was set up in front of the classroom, when I make my diagram, I will still draw it as if it's less than 45. And clearly, just by inspection, you can see that there's a smaller angle than that is. The reason I do that is that when I draw other triangles to break down things into components, I don't want to get confused about where theta is. I don't want to think that that's theta, for example. Right? I want to make sure I can distinguish between the different angles. And the way I do it is by insisting on making triangles that have a small angle and a big angle, so I can just eyeball it and keep track of where theta is. Because sines and cosines get all jumbled and you make mistakes, right? If you can't keep track of where things are. And so it just gives me one more way to get it straight. So I put my angle theta down here. This length over here is the full length of the velocity vector, capital V. And so what do I want? I want, in this equation, the x equation, I want the x component of the velocity. That's this down here. Notice that I put the right angle on the opposite side of the original vector I'm breaking up into components. Right? Here's the original vector, the velocity of the ball. It better be the case that my components are each smaller than the original component. Otherwise, I made some mistake, right? And the way to guarantee that that's true is that the right angle goes on the opposite corner from the original vector. Great. So this is the thing I want. It has length capital V times, is it cosine or sine of theta? Cosine. I think that's right. It's the adjacent over hypotenuse. Great. So that means I want capital V cosine theta. That's my velocity. What else do I need? T. I'll put the parentheses around theta so I don't get confused about the T. Now I'm going to add that last term about the 1/2 AT squared. But what is the acceleration of the ball in the x direction? 0. So there's no extra term here. That's all you get. Right? Projectile motion means in the horizontal direction, you move at a constant, your velocity, the component of your velocity in the horizontal direction is constant. That's what that says. So now we'll do the y direction. Y of the ball. What does that equal? Well, once again, it starts off at 0 because of my choice of coordinates. I like zeros and I can get them. The initial velocity is, so first of all, is the y component going to be positive or negative initial velocity for the ball? Positive, because this vector is pointing up and to the right, and I define my y-axis to go up, so it's got a positive projection on the y-axis. So, and that's a choice of my axis. If I had chosen downward to be my positive y direction, I have a minus sign here. But I have positive because I chose upward to be my positive y direction. So I get positive, and I need this component now. That's, as you all guessed, or didn't guess, as you all figured out, v sine theta. So I've got v sine theta times t. So there's initial velocity, I've got to include it. But now I do have an acceleration. What is the acceleration of the ball as it's flying through the air in the y direction? Yeah, what's the y component of its acceleration? Come on. G, is it positive or negative? Negative, because it's just like the ball, because I defined upward to be my positive y direction. So I'll put a minus sign here, 1/2 g t squared. I think I've got all my equations now. Does everyone agree with this? Any errors? All right, if you see an error, let me know. I think that's right. So now what am I supposed to do? Well, I want to see whether this is true, but I don't know what the time is yet. So one thing I can do is just figure out just from one pair of equations what the time would have to be if it exists. In other words, when is the x value of the ball equal to the x value of the monkey? So often what I do when I have a series of equations is I number them, keep my head straight. See, I've got 4 equations to work with, right? So why don't I combine these things and figure out what I need to know? Let's combine 1 and 3 because they talk about the x components of the two objects in the problem. So I'll actually write on my page, 1 and 3. What do they imply? They imply some new equation. Well, x of the monkey equals L. So I can just stick that in for here and say, let's let, if x of the ball equals x monkey, oops, sorry. So all these things put together, what do I get? I get that x of ball, forget that. That v cos theta t, v times cos theta, all times t hits, this is a special moment of time t hit, equals L. Did I get that right? I got that right. Oh, this is 0, so this is the only thing that survives. That has to equal that. Okay, great. Is that true? Well, sure, it's true at some time. That, in fact, tells us what th has to be. Now I can isolate th and stick it in the other equations and see if I get an answer that makes sense, if I see something that's true or not. So I say, all right, what does th have to be? Th has to be, let's see, L over v cos theta. Is that right? Yeah, I got it right so far. Amazing. All right, so now let's look at the y equations. Same thing. I'm just going to set them equal to each other, again, for the same moment in time t hit, and see if it's true. So what do I get now? It's a little more complicated, right? Now I've got d, oh yeah, the equation's amazing. I'm using equation 2 and 4. It's all about bookkeeping and keeping my head straight. It's most of what I have to do. Once I set the problem up, I've got to keep my wits about me and not, I left out my fraction. G. The typos you make at the board are outrageous. Yeah, or I make anyway. So I got a minus 1/2 g t squared, positive d, and I'm saying that equals all this. Well, this is 0. I'll leave that out. That equals capital V sine of theta times t minus 1/2 g t squared. I mean, see a wonderful thing. So these are both for t hit, right? Well, right away we see that these terms cancel out, and that's great. This is the hairiest term on the page. It's the square of. Can I lift this thing? Yeah, I'll put this back up in a minute when we need it. I'm not going to lift the pump. All right. So these two things cancel out. Makes our life easier. And so now we say, okay, then that means d equals this at t hit, if t hit exists, right? And so let's take this t hit and stick it in here and see if these things, and I can even label these equations if I like. Let's say that's equation 5, that's equation 6. All right, what does 5 and 6 give me? It's all about bookkeeping, right? You put these together and you say, oh, that means that d equals, and actually we're asking the question. We're going to say, is it true, right? That's how we're going to get the answer to this problem. We're going to see whether this is true or not. D equals, or we'll see when it's true. What conditions require it to be true, right? D equals v times, well, we got sine theta, right? And then t hit, what's t hit? Oh, it's L, let's see, L over v cos theta. And so now we see a nice cancellation. The v's cancel out. So our answer's not going to depend on the initial velocity of the ball. And if I put this over here, what I get that d equals L times sine over cosine. What is sine over cosine? Yeah, it's tangent of theta. Well, is d equal to L tangent theta? Let's see. D over L, yeah, tangent of theta is in fact opposite over adjacent, right? And if you forget the definition of tangent, it doesn't matter. You didn't just simplify it. You could have left it as sine over cosine, that's fine. You know what sine is, it's opposite over hypotenuse. You know what cosine is, it's adjacent over hypotenuse. You can figure out what tangent is. So sure enough, d over L is in fact tangent of theta. So this is true. And that says that the monkey does in fact get hit by the ball. So this problem is tricky in a couple ways. Most of the problems you're asked to solve on my test and on your homeworks are of the form, calculate, how long how long will Jimmy have to run before he gets to school? Or how fast does the rocket have to go? Or what's the acceleration or whatever? And the answer is to calculate some quantity. In this problem, to solve it, we had to check and see whether a set of equations, when we combine them, gave a true answer or not. This has a different character to it. I want to show you how that looks when you solve these kind of problems. But anyway, the bottom line is, yes, it's true. It's true independent of theta. This statement is true. Whether or not theta is 20 degrees or 30 degrees or 40 degrees doesn't matter. It's also true no matter how tall the tree was. It could have been any value of d. It could have been any distance away. All that matters is that we set the geometry up right at the beginning. The cannon's pointing directly at the monkey. The monkey starts dropping from rest at the same moment in time that the cannon fires. Right? All that had to be true. But we built that into our equations and our drawings. That's why it was sort of built in, and that's preserved, and that's what makes the answer work out okay. And then we did the demo. It was true. Right? So laws of physics, or at least the motion was as described here. We'll get to laws of physics in about 20 minutes. Okay, so great. What else I want to say about that before the next thing? I wanted to point out, the intuition. So we've calculated it, and I hope you followed that or most of it. This is an idea what to do later if you're confronted with a similar problem. But why is it true intuitively? In the case when we dropped the ball and then shot the ball, remember the intuition there was, the equation of motion in the y direction was the same for the shot and drop balls. So if we took a movie, in any frame of the movie, the shot ball and the drop ball would have the same height at every moment in time. That's why it's equal at the same time. And then for the cart that's going along the horizontal, the cart's going along like that, shoots the ball in the air, right? In that case, it was a vertical line. If you mean a movie, there'd be a vertical line that compares the two. So in this case, why does it work out? It's a little harder to think about. There's no vertical horizontal line you can use, but there is a diagonal line you can use. In other words, like the magical cancellation that made all this work out was the fact that this awful term with the t squared canceled on both sides. So let's take this camera. So for this problem, take a camera that's hanging from the ceiling, and I can hear it falling now, and you drop it at the same time that the monkey's dropped. So, and the camera's making a movie of the whole situation. So it starts off, the cannonball's in the lower right-hand corner, the monkey's in the upper left-hand corner, right? And then you go, right? They all start falling. Well, the camera's going to accelerate with the same acceleration that the monkey is, right? Straight down with an acceleration of 10 meters per second squared. That means that the monkey's going to remain in the upper left-hand corner. His little whiskers might be flying up in the air because of the wind or something, but he's going to stay put in the upper left-hand corner of the picture, right? So here's your movie, right? The monkey's up here, got his ears and whatnot, and he's sitting still in the upper left-hand corner from the perspective of the camera. The camera's accelerating down, right? And what's the ball doing? Well, the ball's just making its merry way along a straight line trajectory from the right-hand lower corner to the upper left-hand corner. Oh, sorry, I can't see past my demo. So the ball's going to do that. So from the perspective of this accelerating downward camera, that's what's going on. And that's a simple intuition. You understand what I'm getting at? The ball, in other words, is accelerating downward, as is the monkey. But if we take a movie of it from a camera that itself is accelerating downward, so we sort of remove that acceleration from our description of what's happening, then what you see is the ball takes a straight line trajectory and runs into the monkey. And it doesn't matter how wide it is here, doesn't matter how tall it is there, doesn't matter what the angle is, doesn't matter how fast the ball's going, right? It's going to eventually hit the monkey. So that's the intuitive way to think about this problem. And it also means that if we drew pictures of it in the original laboratory frame, so the ball's doing this and the monkey's doing this, right? You'd say, the ball starts right here and it's lined up with the monkey. And then a little bit later, the ball's up here, but it's still lined up with the monkey. The ball's down here, but it's still lined up. And it keeps doing that until they run into each other. So, and I never saw this before. When I saw this demo before, I never thought of thinking it. I never realized you could think of it this way. But it may help you think about the problem. Often in physics, the big problem that physicists face is coming up with the right way to view the problem, to see it easy to understand, to come up with the right answer intuitively, before they sit down to do the Harem-Scarum equations and actually come up with the right. Because there's always make mistakes. So the more you can intuit what's going to happen, the easier it is to get the right answer. That said, you should still be able to solve problems without having seen them before and without knowing the answer to start. But the better your intuition is, the more likely you are to avoid all the pitfalls of getting the wrong subscript somewhere, or missing a minus sign, or whatever it is. Plus, it's more fun. It's more fun to do this stuff if you can see how to think about it rather than just doing it as a bookkeeping exercise. But you need to have both those skills ready to do physics really well. So I try to bring up both those things whenever I can, whenever we do a problem in class. All right, so that's the monkey and hunt, right? That's a fun demo, I think. Real quick, so for projectile motion, I've made this comment and I've shown you 4 examples of it now. That there's this profound separation. When you have motion, projectile motion in particular, there's a profound separation between the x and the y axis. And it doesn't matter which x and y axis you choose. You can choose different, you can choose angled axes or horizontal, vertical. But there's a separation. And when we solve the equations, we don't even deal with them as vectors equations. We write them down separately in the x and the y and then combine them as needed, right? Here's a problem that's the classic problem, the problem that people really got interested in a lot of these physics problems. How do you get projectiles to go where you want? When you're shooting at something, you want to hit the thing you want to hit. You don't want to hit the wrong country or whatever. It's awful to think of it that way, but that drives a lot of original progress in physics, even some continuing progress. So what am I going to do? I'm going to make a projectile. Oh, I can't see what I'm doing. Let's see. So I've got a little hose. There it goes. Oh yeah. No one's going to get hurt with this cannon, but so here's the thing. What I'm trying to point out is that there is a separation between x and y, but if I choose different initial velocities, right, different angles for my cannon, right, I get different ranges, I get different distances. And so there's sort of a trade-off between x and y, right? If I angle this thing too much to the side, then I wind up just shooting myself in the foot. It doesn't get very far. Something I'm good at doing. And then if I aim straight up, it doesn't get very far, right? Oop, I can do that. Yeah, it's hazardous. That's why I've got this big splash shield here. So then I go like this. But there's actually, you guys know the answer? Somebody calculated this in high school. What's the optimal angle from the horizontal for this thing to get the biggest range? 45. Everyone knows the answer to that. Yeah, most people know the answer to that. You don't know anything else to do. Yeah, 45. Everyone knows that. It's true. If there's no wind resistance, that's the right answer. But my point of bringing this up is just to say that there is a trade-off between x and y in this problem. Why is that? Oops. It's also a trade-off from leaning too close to the apparatus here. All right. The trade-off is in terms of the initial conditions of the problem. So we're saying, the initial velocity has a magnitude of capital V, say, whatever the speed of the water is coming out of the hose. And by changing it to different angles, there's a trade-off to how far you move, how fast you go to the right, how fast you go up and down. But once you set up the initial problem, once you know the initial x and y, once you know the components are the velocity at the outset, the rest of it you solve it by separating out into x and y separately. See what I'm getting at? You solve it with separate equations for x and y, and you do projectile motion with it. Anyway, so initial conditions can allow you to couple x and y for projectile motion, but then once it started, you can. Here, I'll put this thing down so it doesn't block the board anymore. There we go.